Speakers, and the last talk will be from myself. So I will be discussing about basically the research what we do in my group. So this is my slide. I hope you can see it very well. Everything is good. So just let me give you a brief introduction what exactly we do. So basically, I'm also a part of a State Key Lab. So and today I will be talking about the next generation of display using the quantum dots, right? And why it is important and what it can bring for the display, because display is already very mature, but there is something that you have to improve. So just a bit of introduction of myself. I did my PhD from University of Lucknow in soft condensed matter physics in 2009. Then currently I'm associate professor at the ECE department. I'm also associate director of Center for Display Research and the core member of State Key Lab from display and optoelectronic technologies, and also the member of IAS Center for Quantum Technologies. I'm also departmental safety officer and also the coordinator of international student affairs. And in addition to that, I'm editor-in-chief for Journal of Society for Information Display, which is based in the US, right? So if you want to have more information, you can just go through this link and you can connect to me anytime. So let's talk about the display, what exactly we have done. So display industry is kind of very vibrant industry. In the last 30 years, we came from this big fat TVs, CRT TVs, to the flat screen TV, which is, so right now, your entertainment system, your music system, your banking system, everything can fit into your palm, right? So that is the development of last 30 years. So what will happen in next 30 years? So before that, there is an anecdote that in last 30 years, 20 years, if you compare 1990 and 2017, so basically the TV became flat and we as a human being became fat, right? So that's a very interesting thing. So what is in next 30 years? So in next 30 years, what will happen? That will be decided by the students, by the next generation of students, what you guys will be doing. So what I can do is I can just give you a brief introduction, what exactly where the society is going through. So if you look at in the top left corner, we have LG Canyon, which is basically trying to replace all the walls with the display, with the curved display, flat display, or any shape, whatever is whatever you want. Then the colors become very vibrant. We have quantum dot based monitors. So quantum dot is a nanoparticles, semiconductor nanoparticles that can emit the very pure colors. So the color saturation is significantly high. So you can cover very large area of the human visible sensitivity. So that increases the color saturation, and then you can additionally you will have like sensors in the display. So display will be not only used for the imaging and movies, but you can also use it for the sensing, right? And then the display will be also used as an antenna, Wi-Fi antenna, right? So that means you will show the image, and at the same point of time, it will also communicate, right? In the Li-Fi communication system or Wi-Fi communication system, so it can also be used as an antenna. We have holographic displays coming in, and then we have very hot topic is augmented reality, virtual reality display, doing various kind of things. Then recently, it is a stretchable display. That means the display can be stretched, right? It's stretched just like a clothing. Also nowadays, people are worried about the blue content. So basically, they want to reduce the blue content so that they can save the human eye, right? And then we are trying to transfer this quantum dot, because right now all the displays, whatever is available in the market, they use sheet, very large sheet behind the panel to that sheet has quantum dot, this nanoparticles. So the material consumption is seriously high. So if you want to reduce the material consumption, you can transfer this sheet into the film, into the LEDs, right? And in that case, you can have same optical quality, but you can reduce the material consumption, right? So if you look at all of these things, the main trend is the displays are getting bigger and bigger, and the pixel density is increasing. So the one thing that should be that is a very big question right now is the power consumption, because all of these display, does not matter LCD or OLED, both of them suffer through the low efficiency, typically in the range of 3 to 5%. And if you increase the resolution, increase the pixel density, then the efficiency will drop down further. So right now, if you look at the portable devices or TVs or monitors, this number is not very big. But if you imagine the conditions where you have very large displays around you, then this will be a big thing to worry about. So just to give you an idea, the OLED is increasing significantly, but it's still, the LCD is the market leader with more than 70% market share right now, right? So LCD is still there, and it will be there around for a while. So what we did, we try to understand the power consumption. So we did some sort of analysis. So we try to understand exactly if you display the image, simple image content that has like some text and the graphics, and if you use Wi-Fi network, then for the LCD, the power consumption can be given like that. So you can see here the LCD is consuming a lot of power among, this is the highest power consumption for all the components in the mobile phone, right? And this is the 4919 milliwatt. That is basically the power consumption for the backlight unit. This means the biggest power hungry device in the whole mobile phone is the backlight unit. And if you change the Wi-Fi network to cellular network, so what happens is GSM unit will consume a lot of power, and Wi-Fi power consumption will reduce by a lot, right? But it's still, the backlight unit is still the biggest power consuming component in the whole device. So that means if you, so basically LCD backlight is the biggest culprit for the low efficiency of one of the biggest culprit for the low efficiency of these devices. So we did some calculation based on the data available from the Hong Kong government in 2019. We had like 6.61 million smartphone users. So depending on that, if you consider 2.5 watt for per average power for every display, so you will end up having around 400 to 600 terajoule of energy consumption only for display. It is not talking about any other electronic component in the device, right? So this is a power consumption only for the display. Now, this number is not very big, considering a lot of different things right now. But if you change the display, like you change all the walls, all the tables that you are that you can touch, all the surface that you can touch with the display, then this number will become seriously big. And in addition to that, because it is not very efficient, so it will also heat up the ambience. So in that case, you need to increase the power consumption for the air con as well. So that means we need to find a way to improve the efficiency somehow, right? So I give you an example for the LCD first. So basically we have, this is the typical structure of the LCD. We have a backlight unit, then we have other components over here, and then you get the final image here. So if you consider that backlight unit is as 100%, and you have a lot of different components like the polarizer, color filters, and things like that. So and all of them, they absorb light, right? So by the end of the day, you get only 4.8% of the light. And so that is not good. So if you look at this, there are two major components, color filter and polarizer. So polarizer is responsible for more than 55% of losses, and color filter induce losses of around 70%. So if you can improve these two components, you can increase the efficiency by a lot, right? So our group is basically working on that. So we have worked on the quantum dots for the polarized emission. That technology is already licensed. We also worked on the fast ferroelectric liquid crystals that can remove the color filter losses, and this technology is also licensed partially. Backlight unit is not efficient right now, around 70 to 90 lumen per watt. So now we are working on improving the efficiency more than 200 lumen per watt. And if you can incorporate all of these features, then basically we can increase the efficiency of the display more than 20%. And that is what we are trying to do, right? So this is an overview of research what we do in my group. Polarized losses, use the aligned quantum dots, and then you use the color filter losses you use for field sequential color display, or you use photoluminescence type color filter to improve it, right? So I will just give you a brief introduction. So this is a simple schematic why the light from the quantum dots are polarized. So quantum dots are already in the market, but it has been found that if you use rod shape, then because of the spatial distribution of the excitance, what you can get is the polarized light. And if you can align it over the large area, you can increase the optical coupling efficiency, you can increase the polarization efficiency of the light, and you can make the display more and more efficient. So we did a lot of work on that direction. I will show you some of them. So this is the typical device structure what we can use for the quantum nanomaterials, like a sheet, what is already in the market, already commercialized it. Now the QD on chip. So basically, you place all these nanomaterials on the chip. That is in the process, in the development, and it should hopefully it will be available soon in the near time. Quantum dot color filters on OLEDs already in the market. LCD and LED are still in development. And eventually, the best configuration will be electroluminescence, right? That is what so many people are working on it. And that will people believe, the society believe, will be the ultimate solution for the display application and also lighting application. So as I said, you can align these quantum dots. So we have developed a new approach called as photo alignment of quantum dots that is using the liquid crystal matrix. And by using that, you can align them very, very high quality, and you can have very high polarized light. If you remember the Malus law in your high school, so you can see the emitted light shows very good agreement with the Malus law, which is over here, right? So this is a very good film. So we made a film and compared with the iPhone. And here you can see on the top, we have iPhone 8 Plus, and on the bottom, the display made by our group, right? So you can see the colors are significantly different, and the efficiency is also different. So the iPhone efficiency is around 4.5 to 4.8%, but in our case, the efficiency is around 7.8%, right? So the colors are good, efficiency is almost 2 times better, right? So you can find all the information in this papers, or you can also refer to this YouTube link. So we got very high color saturation and very high efficiency. Then we also wanted to explore if we can use these materials for the lighting, right? Because lighting is a completely different thing. Because right now, if you look at the LED lightings, and if you go to the market and try to buy the LED bulb, you can find the LED bulb with the efficiency of around 100 lumen per watt. Sometimes it is around 75, 80 lumen per watt. But theoretically, the maximum efficiency for this kind of LED bulb can hit around 300 lumen per watt. So ideally, if you can achieve the higher efficiency, but there are some problems because the material what people use is not very efficient. So we try to use our material and see what we can do. So we optimize the material in different ways. We get right now we can achieve around 214 lumen per watt, which is among the highest and reported in the till now, right? And you can have various different kind of spectrum. You can have very different color temperatures and very stable LEDs. So the Department of Energy from US, they set a goal that by 2025 the commercial LED products should have 200 lumen per watt of efficiency. And right now, our results are over here, right? So this is like a around 214 lumen per watt we already achieved. And we are now working towards the 300 lumen per watt and try to understand what kind of device structure we can make to make it more efficient. All right, so electroluminescence, as I said before, which is very interesting. And this is very simple device structure, as Professor Nets mentioned before. You have a charge transporting layer like zinc oxide over here, and then a hole transporting layer over here. And then you have an emitting layer, which is basically made of quantum dots. And if you apply the electric field, you supply the holes and electrons from the electron transporting layer and hole from the hole transporting layer. Then they can meet in the recombination zone right here in the emitting layer and then emit the light, right? That's a simple concept. So we have been demonstrating these LEDs. And we have in the past, in the last year, we demonstrated these LEDs with efficiency of around 9% for red, 6% for green, and 1.3% for blue, which is kind of very challenging, right? So then the idea is basically when you supply, if you look at the device structure like that, so you have ITO, and then on the other side you have silver or aluminum electrode, and then you apply electron from this side and holes from this side. And they travel through all the way from hole transporting layer and hole injection layer and hole transporting layer, and same way other way around from the electron transporting layer, and then they have to meet in the emitting layer right here, right? So they should meet right in this layer. So when you apply the small electric field, this is what happened. They meet right in the middle. If you optimize your device's layer thickness and the smoothness and the material properly, then they will meet in the center. But when you increase the electric field, then what happens is this recombination zone shift towards the whole transporting layer side, and then your efficiency drop down, and also your lifetime will also reduces, right? So we try to optimize the device structure, and now what we can do is, so this is, you can see here the efficiency of the conventional device, which drops if you increase the current from 100 milliampere per centimeter square all the way to 1 ampere per centimeter square current density. Then normally for conventional device, the efficiency dropped down to 70%. But in our devices, after the optimization, this drop is only 5%, right? So this efficiency is pretty good. At the same point of time, the lifetime for these devices is also very high, right? So that means after this new set of optimization, you can have very large, very efficient devices for very, very high brightness, right? So why do you need that? So high brightness are important for the augmented reality display, right? Mixed reality display, where you are in the, sometimes you are in the room light, where the intensities are very small, but sometimes you go outside where the intensities can, the brightness can hit like 10,000 nits, right? So the brightness range varies a lot. So for that kind of application, you need very large brightness from the display. So this is kind of research orientation what we are trying to do right now. Okay, so this is a simple comparison. So we have, our results are over here. We show more than 21% of efficiency with a very high current density. All right. So that's, I think, is my last slide. And with this, I just give you a brief introduction, what kind of research we do. So our group is doing two research. First is the quantum dot display using the various kind of material and device structure, using the electroluminescence or display devices using the photoluminescence. And we also work on the photonics using the ferroelectric liquid crystals. For photonics and display, like here we are showing the LiDAR, which does not require any complicated device structure. It requires simple, very simple Daman grading profile, which is kind of very easy to make. Then we also make some polarization dependent lenses where you can switch the focal plane just by applying the electric field, right? So this is the idea what we can use for the virtual reality. And most recently, we are working on the passive sensors, which does not require any power, right? So usually what you do is you apply the electric field, you get the mechanical vibrations, and then after what you do is you amplify it to send it out somewhere, right? So right now, this development, basically, we do not read any power anymore, right? So that is one of the advantage here. Okay, so here, all the other information you can find in this papers over here, if you are interested. And with this, I will just conclude. These are the all the people who are involved in this kind of research, all the students and the research staff, and of course the grants and the collaborators. And with this, I would like to thank you. And in case you are interested in the research, feel free to contact me. You can visit this link, or you can send me the email directly, right? So with this, I will stop here. And in case you guys have any problem, any questions, you can directly contact me. All right. Okay, so with this, I would like to thank Professor Levent and Professor Christian for your valuable time and contributions. I think we will extract all the information and split this presentation in 3 parts and then upload it on the